So, good morning, everyone. Welcome again to CMMR2023, and welcome to the special session on computational research on music evolution. So, given the situation that a lot of people are interested in AI and especially music generation systems, so let me ask this question. So, can we understand the creativity of JSPAC by realizing a deep learning model imitating JSPAC's composition style? Okay. So if you don't think JSPAC is creative, it's no problem. Please replace this with whoever, any artist you think creative or genius. Okay. So my answer is no. So why? Because I think JSPAC is creative because he did something new, not simply an imitation of some other's work. So to understand, to discuss creativity, the temporal context should be considered. So this is clear. So this is one motivation for thinking about music evolution. And there are many other motivations, but in general, I think to understand musical culture deeply, I think you end up thinking about the historical or evolutionary process. So let's start a session. So we have 5 talks, and actually the first, I am a chairperson, but also a presenter for the first 2 talks. So during this talks, I asked third person, so Satoshi Tojo, to take the role as a chairperson. So.
Okay, I'm a substitute moderator because I myself is a boosted to encourage him to take this special session. I'm much interested in. I'm claiming this is the origin of the music, origin of the language is the music. So we are much interested in evolution. We would like to share common interest.
Test. Perfect. So, good morning, everyone. Our topic is historical changes of modes and the substructure model as patch distribution in Plainchant from the 11th to the 15th century. And so, my name is Tim Eipert, and I'm a PhD student from Würzburg, Germany, and I would like to introduce you to the topic. And first, some context information about the topic of the whole session, some words from me. So when we do copy studies with music, it often concerns the question of style. And music evolution research describes a field of study that deals with changes in musical styles over time. For example, this is a figure from a paper from 2015 that provides a quantitative picture of the evolution of popular music in the USA over 50 years. It shows a clustering, and according to musical features, of approximately 17,000 recordings. Various publications take a music evolution approach to musical styles like folk, world music, Western pop, and classical music. However, Western medieval music is mainly ignored, although the medieval period has exciting and rich questions and data sources. For example, you can see in this figure the distribution of a typical genre and the tropes of medieval liturgical music manuscripts. That are the notes in the network from the 10th to the 13th century. They span over a large Western European area of the so-called Carolingian Empire. And the links between the notes in this figure visualize the repertoire overlaps of the different manuscripts. And in the European Middle Ages, a fixed repertoire of liturgical chants has developed since late antiquity, and it has been transmitted over centuries to all Christian territories. This widespreadness makes it attractive to compare the different versions of the chants. Also, with this repertoire, we can shed light on our understanding of the development of pitch organization in Western music from its earliest beginnings. Modality is a feature of medieval music theory that is especially important for our study. And the large number of chants that has to be learned by every liturgical singer without using any form of musical notation, it's an oral tradition, and created the need to establish an order based on music criteria. Organizing chants is one of the essential functions of the modes emerging that time. We first find such modes in manuscripts with lists of chants called tonary. You can see one here. These group the chant into 8 different categories. In later manuscripts that transmit the melodies, the modes are most clearly distinguished by the final tone with the final D, E, F, and G, and the ambitus of the melody. However, not just the end of the chant plays a role in melody, and it can be assumed that modal characteristics should be reflected in the whole pitch distribution of the chant. And also it is plausible that other criteria, like the liturgical context, play a role in classifying the modes. 2 short mentions of what others have done in this field. One study from Huron and Redman did a clustering of chants, and they found 2 supramodal groups that each shared some melodic features and suggested that this polarization has to do with the evolvement of major and minor tonality in the 17th century. Another study examined mode classification in medieval plainchant melodies using a distributional model, and it achieved a classification F score of over 90%. Both studies try to classify modes by looking at melodic features. Still, they do not consider the manuscript's date of origin. Also, both studies cluster by pitch distribution on the level of mode, but do not consider that there are possible substructures of pitch distribution within the modes. In our study, we incorporate the factor of temporal development. Analyzing the evolution of modes and related pitch distributions leads to addressing 2 central research questions. How did the relative frequencies of modes change over time, and how did the pitch distributions of individual modes change over time? So let us talk about what data we used and how we did it. We derive our dataset from the Cantus database. This project has collected chants since the 80s, containing over 60,000 chants with a melody transcription. We use 3 types of information in particular, and that is melody, mode, and source date. The type of the mode and the source date are self-explaining, I think. The melodies are represented in a specific encoding named Volpiano. And so since we get no information from the manuscript about the sung note's duration and the melody is monophonic, we can easily represent the melody as a string. The 3 different stages are the following. In A, you can see a scan of the original manuscript, and there's just a single staff line in red marking the position of a pitch F. And in B, the melody is represented in this Volpiano encoding, where the pitches are represented by letters ranging from A to P, alongside a modern staff notation for more straightforward interpretation. And finally, the chant pitches in C are displayed using a standard musical notation. So for the study, a subset of the over 60,000 chant entries in Cantus has been selected, and excluding chants with missing data and 2 short melodies. After these pre-processing steps, we still have a dataset of over 40,000 chants for subsequent analysis. Now I hand over.
So I'm Eita Nakamura, and I will explain about the technical aspects of this analysis. So to analyze the mode structure, quantitatively, we construct a generative model of melodies in chants. So first, we can use the Markov model to characterize the pitch distribution of a mode. So more specifically, the transition probabilities of consecutive pitches characterize the mode in this model. So this can be visualized as in this picture, where the white band indicates a large probability. And next to, excuse me, to represent the generative process of chance in multiple modes, we consider multiples of Markov models and the relative frequencies of the modes in this, as in this figure. And this is called a Markov mixture model. So as I explained later, this model can be used for mode classification and clustering of melodies. Now, to consider the substructure of modes, we consider hierarchical Markov mixture model. So this model has two levels of group structure. So the upper level corresponds to the 8 modes, and the lower level groups correspond to the internal clusters within each mode. So the model parameters are the relative frequencies of modes, and the relative frequencies of internal clusters, and the Markov model parameters of each internal cluster. So this model is appropriate for addressing our research questions. So because by analyzing the temporal changes in the the relative frequencies of modes, then we can address the first question, and by analyzing the temporal changes of the relative frequency of internal clusters, we can address the second question. So in our analysis, we first learn the model parameters from data. So since the model labels mode labels are known, so we apply a supervised learning method for learning the Markov mixture model at the mode level. So this can be done by simple samples counting. And next, to learn the internal clusters model, we apply an unsupervised learning method. So this can be, the algorithm can be derived based on the maximum likelihood principle. So we can derive EM algorithm for this. So after learning the parameters, we can apply the model for mode classification by calculating the posterior probability of mode. And also we can analyze the internal cluster structure by calculating the posterior probability of an internal cluster for a chart. Okay. So now we present our results. So this figure shows the obtained internal cluster structures of modes when we assume 3 clusters per mode. So let's have a look, closer look at 2 examples, mode 3 and mode 6. Okay. So in mode 3, although the final is E, we can find the most frequent pitch class as A or C. So there is some variations among the pitch distributions of individual internal clusters. On the other hand, in mode 6, the final is F, and the most frequent pitch class is also F. And there is less in all internal clusters, and there is less variations of pitch distributions among these 3 internal clusters. So this analysis shows that different modes have different degrees of variation of internal clusters, at least by visual inspection. So we performed hierarchical clustering using the pitch distribution and found 2 supramodal groups. So one with mode 1, 4, and 6 as its core members, and the other one with mode 3, 5, and 8 as core members. So this result is consistent with the previous work by Huron and Bertman. Okay, so to quantitatively measure the effects of internal clusters, we evaluated the mode classification accuracy using internal clusters. So the results show that the classification accuracy increases by introducing 3 or more internal clusters. And by inspecting the confusion matrix, we found that the most classification errors occur within each of the 2 supramodal groups. And we also found that relatively high error rates across these groups and between pairs of modes that share the same final tone. So for example, between mode 3 and 4 and mode 5 and 6. Okay.
We have two clustering levels and wanted to investigate the relationship between internal clusters and the genres of chant. So let's look at their correlations. And this figure shows the relationship between internal clusters and the three most frequent genres that cover over 90% of the corpus. That is antiphon, responsory, and its responsory reverse. And what you can see in each internal cluster is the proportion of genre. And most pieces labeled responsory reverse belong to the third internal cluster. This differentiation is due to its musical structure, which markedly deviates from antiphon and responsory. Unlike the antiphon and the responsory, a responsory reverse attaches to one of a collection of formulae patterns that are psalm formulas and does not consistently conclude on the note's final note. Additionally, we observe that each genre exhibits distinct pitch distributions across various musical modes. However, except for mode 6, all modes feature an internal cluster predominantly characterized by the antiphon genre and another predominantly characterized by the responsory genre. And these observations underscore that while the three genres present evident disparities in their pitch characteristics, the clusters generated through unsupervised learning do not precisely correlate with the established genre classifications. Finally, we can relate the internal clustering to time. And it turns out that the changes are really small throughout the analyzed time. The most significant changes are between the 12th and 13th and between the 13th and 14th century, and still the relative changes in the mode frequencies are less than 100%. This stability contrasts sharply with the significant transitions in musical styles noted in Western classical and popular music from the 16th century. However, the internal clusters have larger changes over time. For example, the frequency of cluster 3-3 increased by more than 100% from the 12th century to the 15th century, whereas cluster 1-1 decreased by more than 50% in this period. All internal clusters are present from the 11th century, and no emerge of new groups can be observed, so we have to state that there is no significant innovation in pitch distribution during this time. Now let us summarize and discuss what we did. We identified pitch clusters with the 8 medieval modes and found that they correlate with the major chant genres in the dataset, which makes sense. And so we would expect that the pitch distribution differs, but they did not fit completely. And then we observed stability in the frequency of modes over 5 centuries. And we can relate this to the context of this corpus because it was considered sacred music that comes directly from God and thus must not be altered. So, in the future we need to include location and notational practice features, and also, as always, we want to have more data that we can use to have more valid results. That was our presentation. Thank you very much for listening.
Questions, comments? Ichiro.
What was the last point in your, can you explain that? Down?
The downsampling, maybe.
So I think this is about the temporal information given for this data set. So we have, so chants belong to the manuscript.
Mm-hmm.
A manuscript is given some temporal information. And so by downsampling, we mean that, so we are given like a very coarse temporal information, I mean in time minutes, typically of the order of century. So, but actually, is we can apply more refined method for analyzing temporal structures by so you have an uncertainty of time range. of about 1 century, and then you apply a sampling method, then you can incorporate this ambiguity of temporal information more precisely. So that means that, no, you don't.
I don't understand.
So now we treat this temporal information as a point. But actually, so there is ambiguity of 1 century.
Yes.
So we can consider that this data is spanning a temporal period of time. So the idea is to use this temporal range to better handle the temporal structure.
And generating synthetic pieces, what is that?
Any comments on that?
Are you planning to generate pieces, chant-like melodies? Is that what you mean?
Yes, I think so. Yeah. So,
I think so. Okay, gotta get back to that. Thank you.
Keishi.
Thank you for very interesting. And do you have some implications of development temperament? So, temperament. So based on the analysis results of the temporal context of chant.
could you report because
Do you have any implications to obtain about the development temperament? Tuning.
Well, tuning, no, we don't know about that because it's just an oral practice, and there are treatises about the music theory from ancient Greek, but we don't know how they relate to the practice.
Sure. But just before the ages that 12 tone equal temperament. That is the how.
It won't be a 12 tone equal temperament, maybe, probably.
Thank you.
Thank you.
Maybe interesting application of this analysis is to look at how monophonic music relates to polyphonic music in terms of tonality. Because so specifically with Joskin Research Project, which is like late medieval, it might be interesting to take those data and see. So there's two things. One is in the masses, they usually take an older chant. So maybe an interesting application would be to identify maybe original material in a polyphonic setting, like pre-composed music. And then other was maybe one question is about the final. So does the final always agree with the mode, or is it?
I don't think so, because in the paper we mentioned there's one first experiment with just the final and ambitus, and it doesn't correlate completely.
Yeah.
So it. Yeah.
And then who decides the mode? Is it the encoder or from an early list of the modes?
It depends, and for Cantus it really depends, because sometimes it's in the manuscript itself, sometimes I think it uses lists, and then it could be,
It could be original or it could be
it could
a
be,
modern person deciding.
Yes, but for Cantus, I would think for Cantus it's mostly in the manuscripts.
Okay. Thanks.
Rigorously, time is up. So we'd like to proceed to the next presentation. It's your time again. Okay, please.
Okay, so I'm Eita Nakamura, again from Kyoto University, and in this talk I I'd like to discuss about the evolution chord progressions in popular music. So the chord progression in popular music has an essential role along with the melody. So let me play an example. So this is only melody notes. Okay, so with chord progression, you can add accompaniment. So the chord progression indicates how accompaniments should be played. So we can add accompaniments like this in a systematic way. Okay, so and chord progressions are represented as chord symbol sequences, as in this example. And important feature of chord progression, important for this study, is that chord progressions can be repeatedly used in different songs. So indeed, some chord progressions have been used in many songs. So to quantitatively observe the temporal changes in the populations of the popularities of chord progressions, we can analyze their relative frequencies in each time period. And this graph shows the result extracted from the Japanese popular music data. And we can observe that significant rises and declines of the popularity of individual chord progressions. And we can also find the new progressions persistently invented, and some of them diffuse. And in previous studies, the popularities and historical changes of chord progressions were analyzed, and some evolutionary patterns have been found, but actually little is known about the mechanism of evolution. So by understanding the mechanisms, we want to answer these questions. So can we understand the processes of invention and diffusion in a unified way? And can we predict the future evolution? So to study these questions, we hypothesize that new chord progressions are created by reference and modification processes. And we need to solve two problems to proceed. One is to formulate an appropriate mathematical model for evolution. And the other one is we need to develop a method for inferring the microscopic processes of evolution, because we cannot directly observe how the chord progressions are created. So we use the ideas from biology and also statistical machine learning to solve these problems. The general mathematical framework we use was developed by theoretical biologists. So this theory is based on the analogy between the biological and cultural evolution. So we think that we can understand both cases by studying the iterated processes of information transmission, selection, and mutation. So more specifically, we built a model based on the model of molecular evolution of biology, and where mutation is described as a stochastic process. And it has been applied to evolutionary tree analysis, for example. So a good example of an application is, so we can estimate the time when humans diverged from the primates using this model. So we apply this for chord progression evolution. So now I explain our method. So we represent chord progressions as L-grams of chord symbols, as shown here. And for the analysis, we use the production year of our chord progression, which is the production year of the song. And all chord progressions were normalized to the natural key, C major or A minor, in advance. So our evolutionary model represents the generative process of a new chord progression in two steps. First, a reference chord progression is selected from the pool of past chord progressions. And second, the reference is replicated to create a new one with or without mutation. So these processes are both stochastic. So in the selection process, we consider two biases. So the recency bias represents the tendency that recently used chord progressions are more likely to be selected as a reference. So this is represented as an exponential decaying function, and the frequency-dependent bias. This represents the tendency that frequently used chord progressions are more or less likely to be selected as a reference. So we represent this bias as a power function of the relative frequency of the L-grams. And the exponent, the value of exponent alpha, when it is larger than unity, it represents a conformity bias. If it is less than unity, novelty bias. If it is equal to unity, so this represents a neutral case. So these biases are often used in cultural evolution models, and here the time constant tau and the exponent alpha are unknown parameters, so we need to infer them from the data. And in the mutation process, we consider three possible modes of mutation as shown here. So replication and substitution, deletion, and insertion. So one of these mutation modes is first chosen according to the mutation mode probability. And then in the substitution mode, symbol-wise substitution probabilities represent the probabilities of specific types of substitution. And similarly, as for insertion, the symbol-wise insertion probabilities represent how likely specific chord symbols are inserted after each type of chord symbol. So the mutation mode probabilities and the symbol-wise mutation probabilities are also unknown, so we need to infer these parameters from data. So for the analysis, so we need to estimate the unknown parameters of our model from data, and and also the referenced L-gram of each newly generated L-gram is also unknown. So it is treated as a latent variable. So we apply the statistical machine learning method to infer these from data, basically based on the maximum likelihood principle. So I skipped the details about this method, but we can derive a hybrid algorithm based on EM algorithm and iterative grid search to infer these parameters. And also we apply MC method for calculating the estimation errors of important quantities. So after we obtain the model parameters, we can calculate the posterior probabilities of mutation mode and symbol-wise substitutions and insertions and referenced L-grams. So we use these posterior probabilities to analyze temporal changes of the evolutionary parameters. Now I present the results. So I use a data set of Japanese popular music comprising about 2,400 high sales songs published between 1927 and 2019. This graph shows the number of songs per year, and we use the period from 1960 for the evolutionary analysis. So there are 232 distinct chord symbols, and the number of distinct L-grams are shown here. So the bottom figure shows the yearly number of 4 grams, and we see that 39% of the 4 grams are newly introduced each year on average. Okay, the result of parameter estimation indicated a strong recency bias. So this means that the probability of chord progression being used as a reference decreases by a factor of 10 in every 6.1 years. And for the frequency-dependent bias, a slight conformity bias was indicated, but the deviation from the neutral case is within the statistical error, so we found no significant frequency-dependent bias in this data. And the estimated values of mutation modes are shown here. So we found that the deletion probability is almost 0. So the reason is that the deletion mode has a small number of trainable parameters and a small number of chord progressions that can serve as a reference. So the substitution, excuse me, the substitution and insertion modes have relatively large probabilities, so that the sum of mutation probability is larger than the proportion of new progressions. So this means, according to this analysis, 38% of not strictly new progressions were invented independently, independent mutations. And so this graph shows the temporal changes of the mutation mode probabilities. So we observe that large variations for substitution mode probabilities with some increasing trend, and small variation for insertion probability, where no visible trend was found. And these figures show the symbol-wise mutation probabilities. So we show dominant symbol-wise mutation probabilities and their temporal changes. So significant temporal changes were observed in both substitutions and insertions. And for substitutions, we found that the diversity of substitution types increased over the time. And so we can also see that most substitution types retain the root tone or chord function, so which is in accordance with our intuition on music theory. And as for insertion, most mutation types align with typical chord transitions. So we can also find that major key related pattern, more major key, minor key related patterns in the early period, and more major key related patterns in the later period. So now we come back to our first question, the relation between invention and diffusion. So theoretically, the large mutation rate we found leads to the picture of the diffusion process. So diffusion here means to become common or popular in a sense. So independent mutations accumulate in the pool of chord progressions, and eventually the replication probability increases. So this leads to general tendency that a larger mutation probability indicates a larger probability of diffusion. So to test this expectation, we define the diffuseness as a sum, a time average of replication probability. And as a result, we found a high correlation between the mutation probability and the diffuseness. So even though there is some small variations among the diffuseness in the data, so summary here is that we found that the mutation probability of a chord progression affects its eventual popularity. And the second question, how we can predict the future evolution. So we now learn some ideas from statistical physics to think about the relationships between mutation and fluctuation. So we can expect from the evolutionary theory that the repeated mutations increases corresponding fluctuation, like this picture. So given that selection pressure does not counteract. So taking the counter position of this, we can say that mutations conforming with existing fluctuation may be more successful. Okay, so the point is, according to this theoretical expectation, we may predict the future mutation probability from the existing fluctuation probabilities. Okay. So to validate this expectation, we use calculate the fluctuation probabilities using the data before 2010 and predict the mutation probability in later years. And the results shows we found positive correlation between the substitution probability, the mutation probabilities and the fluctuation probabilities. So we found especially high correlation between insertion probabilities and chord transition probabilities. So we can partly predict mutation probabilities from using fluctuation. So we can also apply this model to predict new chord progressions that will be created in the future. So these are the model's prediction. So this table is also presented in the paper. So let me conclude my talk. So in a broader context, I think this study opened mathematical proposes a mathematical way to uncover the evolution mechanism of Chord progressions. So we developed a method for inferring the selection and mutation processes from data, and we found non-trivial relations between mutation and diffusion, and we showed the potential for predicting the evolutionary process. So caveat here is the result seems very interesting, a lot of suggestive results, but the result does not necessarily prove that the theory or hypothesis here is correct, so we need more evidences in the future. And one thing I want to emphasize is music evolution is a very attractive topic for multidisciplinary research, so CMMR, which stands for so in this study, musical is of course related. We use like machine learning methods, ideas from biology and physics, but also, of course, to understand culture, cognitive and social science are also relevant. So I like to, invite people from all fields to think about music evolution research. So thank you very much.
Thank you for a very interesting presentation. I have two questions. The first one is a technical one. So let's say you're looking at a piece of a song in like 2019, and you're looking at a certain algorithm. Then that algorithm actually could have come from an insertion from a previous one, a deletion of something from a previous, and substitution. Are you counting all the possibility as an actual instance?
Yes.
Okay. Okay, thanks. The second one is, so, of course, you're thinking of those changes as a stochastic process. But actually, for a physicist, stochastic process, we use it actually when we don't know the intentions of the person who's doing it. For instance, if I'm making a song, I'm not stochastically changing a chord that I've heard. Maybe there are some sort of intentions of a creator. So how do you see the relationship between modeling as a stochastic process and trying to understand it as a creative process, which can be intentional?
Yeah, very good question. So to answer that question, there must be, we must do a lot of more research, but I believe that the current framework can be extended to study such more creative aspects. So the current model is a very simplified model, but we can extend that to include, for example, listeners' preferences and creative strategies. So this is a analogy of directional mutation in the case of biology. We also, so this time we analyze the Japanese music data, but so mutations, but actually there is significant influence from Western music, especially United States. So now what we are treating as a mutation can be actually imported or migration. So we can include these aspects and then refine the model. Then that model can be applied to study more like more detailed aspects of evolutionary process. That's what I believe I'm planning to do in the future.
Just one smaller question. So how would you propose actually getting into the composer's brain and trying to understand what's going on there?
So yeah, that's a very deep question. I mean, we cannot do that by doing this kind of data-driven approaches. To do that, of course, we need to also study like cognitive science and neuroscience. So there is a bunch of research fields with multidisciplinary research. So yeah, there are many things to do in each answer.
Okay, thank you.
So using absolute chord labels or relative to a key? So do you transpose before you do the analysis?
Yes.
Did you mention it?
Yes.
Okay.
Oh, yeah.
Not normalized. Yeah. And then one thing, I guess, with intention is, so what I see maybe in the plots, at least the initial one, is maybe a tendency towards like maybe weakening the tonality. So at the beginning in the 50s, maybe very clear sequence like C, G, C. But then over time, you add more and more chords, so similar to jazz, so kind of making it more jazz-like, perhaps. So there's maybe, so it'd be interesting to figure out maybe how this relates maybe to external pressures, like what is the evolutionary pressure that's causing these?
Yeah, so there can be a long discussion about this. Generally, in the history of Japanese popular music, so we started with like more similar to Japanese traditional style of music, like
Also very
pentatonic scale. Generally, the tendency towards westernized musical scales are more complex chord. But I think in the recent year, after the year 2000 or so, I think Japanese popular music evolved in its own way, maybe more complex than jazz music actually. So that point is a really interesting point, and maybe I will talk in the future. Thank you.
I'm sorry. And the time is up, but this is my privilege to ask you questions. In this occasion, I'm just a substitute moderator, but very general question. That is, you have defined the cultural evolution on page 5, I remember. The evolution is a result of the natural selection that is survives, that is adequate to the environment. But you have introduced such a kind of some conformity or recency or like that. What is the difference, that the criteria for the distinguish that is evolution and just haphazard fluctuation, the change of the fashion, change of the style?
I don't really get it.
You don't have to claim to it's an evolution. It must be adequate to something.
Financial.
Financial.
So it's the top rated.
Okay.
Yeah, financial or well, but I mean, we must. I have to say a caution here. Evolution means a very neutral case in biological science and physical science. It is actually a substitute for temporal changes only. So it's not progression. It does not mean progression. But sometimes, of course, we have natural selection process, or in the case of culture, we have social selection. I mean, the big cells musical style may be imitated in the future more. That kind of selection process is also important, but not necessary. So I mean, the random fluctuation effect is also an aspect of evolution.
So I'd like to change the moderator from me to you.
Thank you. Presentation is by Marco Buongiorno Nardelli. The title is Network Approach to Harmonic Evolution and Complexity in Western Classical Music.
Thank you. Yes, I'm Marco Buongiorno Nardelli. I'm from the University of North Texas and the Santa Fe Institute. And for those of you who were at the concert yesterday, this is what I mentioned is the immersive room in Milan where the piece was performed first. So, in this talk I will focus on the idea of networks of music, but I will not actually go into the details. I'll just show you the kind of the titles of 3 papers that I published in the past years, where I build this concept of representing musical spaces as networks. And when I say musical spaces, I talk about musical spaces of pitch, of chords, so harmony, melody, timbre, orchestration, performance. So it's a very wide range of applications that this network theory of music can be used for. So this is the first paper where I introduce the concept. This is the second paper where I'll actually touch upon some of these ideas in the next few graphs, where I basically extract the kind of the information out of this representation. And then the third one is the more mathematical, and the one that I will be using to discuss the idea of music evolution, or a measure of music evolution using this kind of representations. Now, since a picture is more than 1,000 words, and music is more than a picture, I want to play this short movie to give you an idea what I mean by network representation of a musical space. So this is one of the 366 Bach chorales or whatever they are, how many they are. This representation is an automatic, extracted automatically from a score. And the colors that you see, so basically the nodes of this network are the chords, the chord progressions. The links are the directional links between one chord and the next. The thickness of the link is how many times this progression happens. And the colors are automatically generated from an analysis of community structure. So this is not something that I colored. It's something that a statistical analysis does. And as you probably have noticed, different colors correspond to different tonal centers in this representation. So this is the kind of information that we get out of this representation. So one of the things that I'm interested in talking about today is how out of this kind of representation you get information about musical ideas, musical concept, and in particular how you can see tonal harmony as an emergent property of a complex network. So this is the process that I do for creating these networks. This is the process that was used to generate the previous video. And this is done on a score of one of the late Bedouin string projects. This is the network representation. So each node you see corresponds to a particular chord, represented as a vector, and then you have all these transitions from one chord to the next. Now, the topological characteristics of this network are can be quantified through the degree distribution of the node, so how many connections a single node has with other nodes, the modularity classes, this community structure that emerges from the analysis of the network itself, the fact that we have directional and asymmetric links, and that this structure is repeated at different scales. So it's not just a global property, but it's a property of the network in itself. These kind of networks have a particular characteristics. They are called scale-free networks, and they are super common everywhere. Facebook, Twitter are scale-free networks. There are models that have been developed to describe this kind of networks, but I will not go into the discussion of this. What I want to say here is that if you look at the characteristics of the network as a statistical object and you map them onto the characteristics of tonal harmony, you have a one-to-one correspondence between those quantitative measures and the characteristics of what we study in school for common practice harmony. So tonal harmony is governed by central chords. There is a hierarchical structures of the chords. There is asymmetric. The progressions are asymmetric, and there are hierarchical relationships all around at each level in the composition. So this is one kind of information that is extracted just by this kind of snapshot of a piece of music represented as a network. But as we were saying earlier, temporal devolution is central to music, so we can look at the same score, and now we can look at the progressions as a score time series, so that we look at how the different chords are introduced and then reused over time, and we can apply segmentation algorithms that are always been derived for the analysis of time series for any kind of time series, stock markets, whatever. And kind of classify the different areas of these time series. And if we do so, we realize that we can build a temporal network where each layer corresponds to a particular segment of the time series and correspond itself to a particular key region or tonal region of the piece. So here we have a network structure that corresponds, say, to a E flat major area, and then you evolve into a G minor area, and you see the relative importance of the different chords that changing going from one to the other. So not only information about the key itself, but also how the progressions and the tonal centers evolve in the composition. So there is a lot of information that we can gain out of this representation, but what I want to discuss now is how we can quantify this information and extract or distill a descriptor that I would call say complexity, a measure of complexity of what we are looking at in this piece. So I want to make a clarification here. Complexity doesn't mean complications here. So we are not talking about how complicated a piece is. We are talking about complexity as a measure of, say, how you would place a system in a scale that has, on one hand, a completely random system and a completely ordered system. So if you think about an image, you have a white noise image and a solid color, and you are trying to place where in this range a particular piece of music is, and see if we can get some sort of, some information about the evolution of how this complexity changes over time. So I will start with two, I'm using different methods to evaluate complexity. They are all based on the theory of information, so some sort of information entropy. These are the references that if you are interested, we can talk more. I don't want to go too much into the details of this, given to the limited time, but the important idea here is that this kind of representation in terms of networks supports an interpretation in terms of information processing. So I use three different measures, so three independent measures on different data sets actually. So the first two, just a KL divergence on the network structure, so on the structure of the connections, the adjacency matrix that is used, that is extracted from the snapshot of the network as a whole. I use a diffusion entropy analysis technique to look at the temporal evolution, so the time series of the score, and then I'll touch briefly on a different kind of measure that depends, that is based on a completely different set of data. But let's look at the results. So this is a snapshot of this complexity measure going from Josquin-Debré to Mahler, so it spans basically the whole. There are not very many composers here, and this is just a preliminary analysis. But what you can see is that definitely, okay, here your reference is basically 0.5 is your random, 1 is your uniform data, and you can see that indeed we see an evolution, a time evolution in this measurement that implies some sort of, in a way, cultural evolution, a way in which harmony evolves over time. The same data, the same composer in the KL divergence. Now the data go the other way, but that's because the way in which we normalize the scale. Again, this data kind of agree with each other, so two different measures give us the same behavior. The problem with this is that we have limited data because we base everything on scores, and there are not an infinite number of scores that have been digitized that we can use. And it doesn't have, and it's very abstract because what you read when you read the score, you read the notes that are there, but you don't hear the performance. In the performance, there are differences that are not captured in the paper. So we want to move from this kind of static and dynamic picture to a completely different data set and use a different quantitative information that is what we call the computable information density that I was in one of the other pictures, slides. That is basically the ratio between a lossless compression of the data against the original data. So we are talking about measurement of file size in a way, or how you can compress your data in the most efficient way. And the good thing is that we can access the Spotify database and use their data on the analysis record that gives us information about, most importantly, the chroma vector for each track. So we are talking about billions of tracks and billions of chroma vectors. So the chroma vector is an interesting object because depending on how you read it, you have information on, say, the harmony, the harmonic evolution of the piece, or the way in which pitches are distributed. And so basically you can look at this information density quantity as an overall kind of measure, but then you can correlate this with, say, correlation length between chords or in the pitch distribution. So we did I did the same kind of analysis, and I get again data that kind of confirmed the previous analysis that we did on scores. And here I want to point out, just to conclude, this data for Schoenberg. So Schoenberg, as many of you probably know very well, went through a very distinct transition between a very kind of post-late romantic tonal music into 12-top composition. And here you see the distribution of this complexity measure pre-1913 and post-1913, and you see how the complexity changes within the same author. So this kind of analysis can also be used to analyze a single composer production and see how the production evolves. So to conclude, all the tools are that I use are in this library. This is called Music Network. It's available on GitHub, and all the information on my website is here. Thank you very much.
Thank you very much for the very interesting talk. So now, questions from okay, so.
Thank you for the talk, very interesting. I have a question regarding the different function of chords in different tonal centers. So, like a chord can mean something in a certain tonal center or something else. I see that in your image, even if the first example this was happening once, like is it something that could like disturb your analysis, or is it something that we could separate into chords, or is it better to keep it as unified chord? I don't know if you have opinions about this.
You mean in a description like this one?
Yeah, even in the first example of Bach music that you played, for example, there was one chord of another tonal center that was just passing one moment and then came back. And then, so it was not really on this tonal center, it was just...
because those are the chords that kind of, I mean, you can see from this kind of time evolution where you have common chords, right, in tonal music that you use for... That you use as pivots or that determine the way in which you evolve from one place to another place. And this is completely captured by this model.
Yeah, exactly. I mean, if you are using this as a passage for another, level.
Yeah.
It's super nice.
Yeah.
What I don't know what I get as intuition is that sometimes it's like a chord can just mean something else if you are in another level.
Yeah.
And then it should be maybe treated differently in different levels.
I don't have the data here in this presentation, but you can translate this in terms of Roman numeral analysis, and you use the layers as your key identifiers, and then you just you map the chords to Roman numerals, and it works with an 80% accuracy against the human analysis.
Okay, thank you.
Thank you for presentations. I just have a very general questions about your network. So I just want to try to understand, like, what's the benefit to construct such a network? So what can we gain for it? Can we use it to like describe a summarization of a songs? For example, we can simplify a lot of like low-level features to high-level music features, but we can make it in a very simple way and abstract it.
Yes. I mean, all of this. The origin of all this work is because I wanted to use it. I mean, it has a compositional goal. So this was originally developed for composing before I moved into this kind of analysis. But I think that for me the most important kind of overall concept is this concept of, in the context of this representation, is the fact that these networks have a common topology that I can exploit, translating this from, say, a tonal environment to a completely different one that has the same topological characteristics but not the same notes in a way.
Okay. Also, I have seen in your previous slide, which you have a lot of different like, points, right? And you have grouped them in different colors. I'm just trying to want to understand.
This one?
No, I think in the previous, very first one, where you play a music and there's a dot moving on. Yeah, this one. So does the same color has extra special meaning? Like for example, green and blue. I understand that.
Yes.
So
I mean, this is what I was saying. That this kind of analysis is not something that I do by hand. This is something that you do. You apply algorithms to the networks. And the algorithm will tell you what are like the chord, say in this case, the nodes that are more connected to each other.
okay.
And those are what like these community structures. It's called modularity in this case. But there are many different algorithms you can use that been developed over the years. And so the different colors identify already the three different key areas that Bach uses in this chorale.
Okay. Thank you.
Thank you. Maybe Ashil's question?
Thanks for that talk. So I'd like to start by saying I always thought Mark Newman tried to ban the use of word scale-free network from Santa Fe.
Yeah, I know. Yeah, well, I mean, Mark Newman is a good friend of mine, and we are. I mean, I direct a working group at Santa Fe on music complexity. He's part of this working group.
Yeah. So I was joking.
Yeah.
Secondly, you actually showed John Cage next to Schoenberg in terms of the complexity. I was trying to say, I mean, it kind of feels like Schoenberg actually was the starter of this revolution made in complexity. Can you actually do a similar analysis for other sort of composers like Stravinsky, who actually
yes. I mean,
was a progenitor of modern music?
I mean, I did analysis on Ligeti's music, for instance. I have a couple of examples, Lux Eterna and the Desorto, the first piano prelude, and you see a completely different structure.
Can you also say that, for instance, John Cage was influenced by Schoenberg? Can you actually say that with some confidence?
I mean, in the musicological context, you can say whatever you want because you can analyze the music itself. I don't know because we didn't do enough work on this if we can extract this information from the data itself.
Okay, thank you very much. So let's thank Mark again for the great talk. Okay, so let's move on to the next presentation by Hara Kim and Yoo-Young Park. And the title is On the Analysis of Voice and Novelty in Classical Piano Music.
very much for the kind introduction. Hello everyone, my name is Hala Kim. I'm from KAIST, Daejeon, South Korea. The title of my presentation is on the analysis of voicing novelty in classical piano music. Okay, so let's get started. So I have a strong interest in music composition, particularly in quantifying how we can compose music in more novel and creative ways. So this presentation is part of my research, exploring this kind of curiosity. So I personally think that composition is a process of conditional problem solving. It's about selecting and arranging various elements, musical elements such as melody, rhythm, or harmony. But I decided to focus on voicing in this presentation because I thought that voicing is a very strong indicator of a particular style of a composer or historical period. So yeah, the voicing is the way harmony is expressed. So I believe it strongly represents the musical style. For example, when transitioning from G7 chord consisting of notes F, G, and B to a chord consisting of notes C and E, even with the same harmony progression, the exact voicing can be varied depending on the composer's style, as you can see on the bottom score. So basically, in this study, we're assuming that composers first select the musical elements and then determine the vertical arrangement of the pitch class set. So there haven't been so many computational studies on voicing practices. There was a study predicting the next voicing using predefined features. But other than this, not so much has been done about voicing itself. Well, in the field of music evolution, there has been a lot of research analyzing music evolution using MIDI or audio features. But voicing has not yet been explored in terms of stylistic evolution, so we decided to investigate how voicing has evolved in classical music. So our data set consists of 1,011 classical piano compositions in MIDI format. We collected from various internet sources, and the metadata such as composition year or historical periods to which composer belongs to was obtained from the website allmusic.com. And to begin with, we conducted key normalization to treat elements that serve the same harmonic function consistently, regardless of the absolute pitch. The key of each composition was determined using Crom-Hansel-Schumacher key detection algorithm. After finding the key, all major key compositions were transposed to C major and minor key compositions to A minor. Yeah, and for songs where key changes were frequent, so algorithm's accuracy was low, the key transposition was not conducted. Yes, so as a result, as shown in the right-hand side figure, histogram, even after the key normalization, we can see that there are still a lot of flat and sharp notes present. So to address voicing, we encoded it appropriately. Firstly, we treated simultaneously played notes in the score as a single unit, which we refer to as a cohort, and considered this as individual units of harmony. Then we represented voicing by encoding the pitch class interval between the vertically adjacent notes, starting from the pitch class of the bottom note. So, for example, if you see the first one, do, mi, sol, right there, we can encode it. We can encode the voicing of that as 0, 4, 3, and the pitch class set would be all the same. So when it comes to voicing, the orders of the numbers is important, so we use parentheses, which means tuple. And when it comes to pitch class set, the order of the number is not important, so we use set symbol. Now we can calculate voicing novelty, as we are assuming that composers first chooses the pitch class set, which is harmonic skeleton, and then determines the voicing. We can calculate the probability of choosing a voicing, specific voicing Vi, given a PC set Si. So that's the equation, and V of Si means all possible set of voicings that can be created from the PC set Si. Yes. Okay. And the V of Si, we calculated this count as the all possible cases achievable with PC set Si on the 88 piano keys in the keyboard. Then the probability of a single composition can be written as the product of the probabilities using first order Markov chain. And based on the information theory, we calculated the log of inverse probabilities, which is the measure of unexpectedness, and we normalized it by the length of the composition. Similarly, we can also calculate how novel the PC set itself is. And this is for the comparison with the voicing novelty, which I will explain further in the following slides. So this is the overview of the code words, PC sets, and voicings. So there are a total of about 1 million code words, and unique number of PC sets were 4,000, and unique number of voicings was 200,000. Yes, and if you see on the figure right-hand side, the pitch class distribution is highly skewed. So x-axis means the frequency. So it means that a very tiny portion of the PC set is heavily used, while the majority is rarely used. And I plotted the I plotted the voicing of two representative PC sets, which is 047 and 049, which is Do Mi Sol, La Do Mi. So the voicing, the distribution of voicing is less skewed than that of PC set. So the table on the left-hand side shows the top 5 PC sets and the voicings of each Do Mi Sol and La Do Mi. An interesting point to note is that the most frequently used voicings were reversed voicings, where the root note of the harmony is not at the bottom. Okay, so this is the main figure we want to discuss. The figure shows PC set novelty and voicing novelty for all composers. Composers on the x-axis are sorted based on the average years of birth and death. So let's see the PC set novelty first, which is pink color. Composers like Couperin and Handel showed a high level of PC set novelty because their compositions are located in the very beginning of the timeline in our data set. Despite being early composers, however, PC set novelty can be low. While Handel and Couperin shows high level of PC set novelty, Bach, for example, shows very low PC set novelty. This shows that Bach has a very strong propensity for using the conventional PC sets when composing. And later composers such as Elgar, Berg, Schoenberg, and Messiaen showed high PC set novelty because they introduced new PC sets. So generally, popular PC sets in classical music were introduced by the very first composer, for example, Baroque period, and then experimental new PC sets were explored by later composers. And in case of voicing, before we dive into the plot, we have to discuss what can make voicing novelty high. So there are 2 scenarios when voicing novelty can be evaluated high. One is voicing novelty can rise only by virtue of the novel PC set, or it can also increase if a composer uses new vertical arrangement of the PC set or using conventional PC set. Yes. In order to identify the driving cause behind high voicing novelty, we additionally computed new PC set ratio and new voicing ratio. new PC set ratio is the number of novel PC sets divided by total number of PC sets. So it's just how innovative PC sets a composer used. And new voicing ratio is the number of novel voicings whose PC set is conventional divided by total unique number of voicings. So it is the pure amount of novel voicings with conventional PC set. Now let's go back to the plot again. Handel's new PC set is the highest because Handel's compositions are the very beginning of the timeline in our data set, as I've mentioned. And we can see that composers such as Elgar Berg, Schoenberg introduced new PC sets, which would have affected their high voicing novelty. However, most composers are in the case where new voicing ratio is high, whereas new voicing ratio, new PC set ratio is low. The majority enhance the novelty of chordal expressions by creatively reconfiguring existing PC set tones. Well, for example, if you see Brahms and Beethoven compared to Beethoven, although he rarely tried new PC set, Brahms had a greater ratio of new voicings, so that resulted in a higher level of high voicing novelty. The same story can hold for Liszt or Dvorak compared to Beethoven. So this could be said as the case where composers generally push the creative boundaries of voicing. So here's the main takeaways. We calculated voicing novelty and PC set novelty and compared them to see how composers make their compositions, how to choose notes as harmonic skeletons and vertically arrange selected notes. So of course, it has some limitations. The exact values we cannot. We only have to compare the relative positions of rankings of the composers to see who is the more creative in terms of PC set and voicing. But at least we provided some frameworks to see how novel and creative the composer was in terms of PC set and voicing. Thank you very much for your attention. Thank you.
Thank you very much. So, questions?
Hi. So it's kind of, to me, I think that the thing that would be kind of more interesting in this context is to look at voice leading rather than voicing because voice leading is the process, right? So in an harmonic evolution, the voice leadings change and give rise to other voicing of the same chords.
Yeah, that's very interesting point. Yeah, voice leading, I tried to consider that at first. Yeah, there is other study which calculates the voice leading probabilities, but in this study I tried to focus on how composers vertically arrange the notes in the same simultaneously played notes. So yeah, voice leading might be more interesting because, as you know, there are very representative voice leadings like G7 to C major. Yeah, that could be great point to dive into.
Yeah, I mean, we can talk later, but with the network representation I was talking about, you can actually get the voice leadings for free.
Yeah, sure.
Of the voice leadings, it's one of the outcome of the calculations.
Yes.
Other questions?
Hello, thank you for this very interesting presentation. My question is on how you calculate the PC set. So it's like a quantification of every simultaneous note occurrence in the data set, right?
For simultaneously played notes, which we call Chord, we just extract the pitch class set.
Right. So this So this goes to this process of creating. So then, for example, if you take a fugue, you will have passages, when you consider it this way, that will have different PC sets that will go as well into the atonal, right? So the variety of the PC sets that you get for data sets with a lot of movement will be very, very varied, not reflective to the tonal content of the piece because of all the passing notes that are happening.
Yeah, a lot of passing notes can be included in all code words. So yeah, a lot of combinations of notes can be made, as you said.
Yes.
Yeah, but here we just take into account what has played simultaneously. Just yes.
Yeah. It's about the comparative analysis, because when you do the comparative analysis and you say what the variety of the pieces sets are, you're not taking into account duration of every chord that is happening. You're only taking occurrence.
Yeah.
So what is happening is you're finding a large variety of different pieces sets happening, for example, already in Bach, that may match the variety of happening in Schoenberg, but the tonal content of both is very, very different. It's not criticizing, it's about the comparative analysis, so there is no information about duration in this representation. And generally in the graph-based representations where you're taking by occurrence of notes and pieces sets. So when you're doing the comparative analysis, there's a basic consideration to say, but in the voicing part, that is very interesting to say how the voicing changes in basic pieces sets. But the variability of different pieces sets is not very valid when you're not considering duration.
Yeah, I got your point.
Just the start.
Yeah.
Thank you.
Okay. So, any other questions?
Hi, thank you for the presentation. My question may be a little related to the previous one. I'm thinking about one of the first pictures you showed that showed how you cut the piece into parts so that you can this one. So I was wondering how exactly you do the cutting. For example, if you have I don't know, a whole note on its own, do you count it as just one chord, or do you do a slice every time a new event happens? And I'm wondering also how that affects the number of occurrences of a chord, because for instance here you have several occurrences of the same chord, but it's just one occurrence of the chord.
Yeah, that's right. In this study, I make every single code word every time the note on events occurred. So this code word would be a single code word, and also that this time a new code word is made. But as you said, this is the same code word, right? Yeah, I know. But to take into account, as music is art of temporal, so every time the sound is made, I thought it would be reasonable to take into account all the corresponding sounding notes every time when the sound happens. Yeah.
Thank you.
Thank you. Are there any other questions? We have 1 minute, a very short question.
Could you
explain more the layout of the horizontal axis on the second to last slide with the voicing novelty? So one of these two. So what is the horizontal axis? So is it supposed to be time?
Horizontal axis is
Then the question is
time.
And then the question is, what time unit? Is it the birthday of the composer, the composition date of the music? So if it's novelty, the question is, you could have like the date of the composer's birth versus the date of the composition are different.
Yeah.
And if it's novelty is the first time it occurs, it would be the composition of the composition date.
I should have plotted the figure by the average years of the actual composition in the data set. Yeah, so you're right.
So you use the composition date.
Here the average year of birth and death year. So that's why the handle might be should have been the first position.
Yeah.
Yeah, but
so you live very long.
Yeah. It's just the problem of
Yeah. Thanks.
Okay. Thank you. So thank you again for the interesting talk. Okay. So next is the last talk of this session. The presenter is Dongju Park, and the title is Bipartite Network Analysis of the Stylistic Evolution of Sample-Based Music.
Okay, hello. I'm Dongju Park from KAIST, South Korea. Today, I will be presenting on the topic Bipartite network analysis of the stylistic evolution of sample-based music. This is the table of contents from today's presentation, and in the introduction session, we will discuss the motivation behind this study and related work. This study focuses on musical sampling. Musical sampling is the practice of incorporating segments of pre-existing audio recordings into new compositions. Musical sampling was used in experimental music in the mid-20th century and became a major formulation of hip-hop and electronic music in the 80s. Where we get interested in sample-based music is the identity of sample-based music is profoundly related to the songs that were sampled. For example, G-funk, the dominant subgenre in West Coast hip-hop during the 90s, created its own group by sampling George Clinton and other funk musicians. So, the sampling practice of an artist reflects the characteristics of the subgenre or the music community to which the artist belongs. So our curiosity is, what if we group artists with similar sampling patterns? We might get a group of artists who are closely related musically. This is the motivation for this study. There have been studies that quantitatively analyze sampling relationships. Brian and Wang created a network of sampling relationships between songs and then used the collapse and sum approach to transform it into networks connecting artists and genres. From that research, we were able to get ideas for using network analysis. However, it's challenging to extract a group of similar artists in the artist network in that study. For example, hip-hop artists may have sampled numerous funk artists, but it's not easy to consider hip-hop and funk as belonging to the same group. In our study, we proposed a new network construction method that better reflects the similarity between artists. From now on, I will explain the methodology of this study. In this study, we merged two data sets for our analysis. The first data set consists of music sampling data collected from the Who Sampled website. Each of the data represents a sampling relationship between two songs and includes metadata for each song. We collected sampling cases from popular music spanning from 1980 to 2019. The second data set consists of artist style tags collected from the AllMusic Guide. This data set provides more detailed subgenre information of artists. Next, I will explain the network construction. A bipartite network is a type of network in which there are two types of nodes and edges only exist between nodes of different types. The network in this study is composed of two types of nodes, artist nodes and sample nodes. An edge is formed between artist node and sample node when the artist has sampled a particular sample. And we divided the entire data set into 8 generations based on the year of sampling, with each generation spanning 5 years. For each generation, we constructed an artist sample bipartite network. Now I will discuss the community detection approach. In network analysis methodology, there is a metric called network modularity that measures the degree of modularity within a specific partition of the network. The definition of modularity is as follows, and it quantifies how many more edges are within a community compared to random cases. In our study, we utilized the modularity formula for bipartite networks. The community structure can be derived by finding the partition of network that maximize network modularity. For modularity maximization, we chose the Bipartite algorithm, which is known for its heuristic approach using a bottom-up method and is computationally efficient. The communities obtained as a result of Bipartite include nodes from both types in the Bipartite network. Therefore, the communities in our study consist of artist nodes and the sample nodes they primarily sampled. As a result, we can make the assumption that the musical characteristics of each community are determined by the set of samples they contain. Under this assumption, the similarity between two communities belonging to different generations can be measured by the extent to which they share samples. To account for the importance of each sample within a community, we newly define the similarity metric between communities using Hitch scores. Now, I will explain the results of the analysis. The results of community detection for each generation are as follows. The number of nodes shows an increasing trend, while the number of edges fluctuates. Additionally, the number of communities steadily increases. When looking at the modularity values, it's noteworthy that the best modularity values for all generations exceed 0.3. In network analysis, a modularity value above 0.3 implies a clear community structures. So we can conclude that the sample-based music network shows a clear community structure. The table in this slide illustrates how to examine the details of communities. This table represents the top 4 communities for the 1995 to 1999 generation. It's interesting to note that in Community 0 and Community 3, the distinction between East and West in hip-hop music is evident even within the sampling communities. Since each community is also a bipartite network, sorting nodes by degree centrality for each type allows us to identify influential nodes within the community. Additionally, by investigating the style tags of artist nodes within the community, we can tag the major subgenres that each community represents. With the similarity metric between communities from different generations, we can create a similarity network to explore the connections and trends across generations. Defining primary communities as those occupying more than 1% of the whole network within each generation is a sensible approach to identify significant trends. In network visualization, the thickness of edges is proportional to similarity, and we apply the threshold to visualize all the edges with a similarity above a certain level. In this figure, a threshold value is 0.2. Since we have information about the main subgenres of the primary communities, we can explore the main branches of sample-based music by connecting this information to the similarity network shown earlier. In the discussion section, we will discuss three major branches of sample-based music that emerged from our analysis. At first, the path from community 0_9094 to 2_1519 represents the subgenres of electronic music, especially jungle and drum and bass. Jungle and drum and bass are genres rooted in breakbeats, where breakbeats involve cutting and repeating the drum breaks from African American music like funk, jazz, and R&B. The fact that the edges in this path have high similarity rates suggests the enduring presence of core drum breaks used in the jungle and drum and bass across generations. The second major branch is classic hip-hop. Since the predecessors of community 1_9599 represents the old school hip-hop, we can say that the successors in community 1_9599 are retaining the essence of old school hip-hop. This is why I named this branch classic hip-hop. One interesting fact to note is that the path starting from community 2_0509 is dominated by Polish hip-hop artists. This suggests that in recent times, classic hip-hop style might be more prominent in European countries like Poland compared to the United States. Lastly, the path from community 0_8084 to 14_9599 represents reggae music. In fact, reggae is a genre that has been using sampling techniques since before the inception of hip-hop music. The fact that the path does not continue beyond the 2000s suggests that there may have been changes in the composition of reggae music and its sampling practices in the post-2000 era. Finally, I will discuss future work before concluding the presentation. Firstly, in this study, we focused on analyzing the similarity between communities from consecutive generations. In future work, we can consider examining the similarity between communities separated by more than one generation. Secondly, the methodology used in this study is not limited to the analysis of sample-based music, but can also serve as a framework for understanding cultural evolution. Therefore, it can be applied to various other domains. This is the end of my presentation, and thank you for listening.
much for the very interesting analysis. So are there any questions?
Thank you for the really, really interesting presentation. And for the genres that were used, did you find jazz in particular? Because I think that is a genre that is often used from the 90s on. Did you find jazz in the genre? Or wasn't it? Because I think, yeah.
I know that in jazz there are so many standards, and jazz musicians replay the standard, but in our analysis, I don't consider like replay. So yeah.
Okay, thank you.
Okay. So, can I ask a question? So, in your method for community detection, can you explain? So, yeah, this maybe is showing this result. So, yeah, I was the network figure. So, maybe can you show the network figure? Yeah. So here, so I understand that you divided the time period into window length of 5 years, right? So are the detected communities in different periods connected afterwards this community detection, or it is done jointly with the community detection algorithm?
I consider the dynamic community detection same as you. But this study I consider the discrete period or period, and I capture the yes, I want to try to dynamic community detection in which ones.
Okay. So by doing that, maybe you can remove the reliance on this choice of the window length, maybe 5 years.
I already considered another width for period, or like 4 or 8, 10, 2. But I think 10 is too long, and 5 is very intuitive or good.
Okay. So
so
analysis decided the 5 years. So when you take this, for example, 10 years, so I presume that you can have a lot of communities detected, and then it's more harder to relate the communities across different time periods. Maybe we can discuss it. So, do you have any questions?
So just my curiosity, and is there any possibilities where a hip hop musician takes a short music clip from the other hip hop musicians?
Of course, there are so many bad cases you say. So
if it is true, so bipartite analysis is effective such a situation. So to the best of my understanding, the ABCD group maybe takes a music clip from the some of the ABCD group.
So good.
So in your slide, anyway, the explanation of bipartite network and the upper layer 1, 2, 3, 4, some the ABCD E,
Yes.
and maybe ABCE represent the members of hip hop musicians, and
Sure.
some of the they may happen. A takes a B script, and C takes a B script.
Yes, you're right. So, there is the possibility, and like B which in songs list, they can have these songs, but I just distinct the artist role and sample role. So yes, so yeah, it is possible, but
So I would like to know can you discriminate such a phenomena from the other phenomena? Or you have a hypothesis that you can discriminate or classify the groups of the hip hop musicians or the generations or clusters, the casting into such a
yes. In my analysis, included hip hop, analysis of hip hop, and of course I can only if I only consider the hip hop songs or samples, then it is more focused on hip hop, and it works. Thank you for your great question.
Okay, thank you very much. I'd like to conclude this session. So I noticed that actually, so most of the presenters of this session are from physics field, including me. So they use difficult methodology. So maybe your methods were too difficult for some of you. So maybe you can ask the presenters later during the coffee break session. So thank you very much for all the presenters and all the participants. yeah, but that is very important thing. I mean, for example, performance expression response to continuous features. So, yeah, I'm also considering like performance expression or audio features, timing also, camera features. I didn't have it's really
your question at 11:30, so and so there is a timekeeper. Who's timekeeper? He's timekeeper. And Mike man, quick man.
There's a
I don't know how long.
I'm afraid because when he starts saving energy, I'm unable to cut that, so sometimes it gets really slow, and it's just to prevent that I have enough time.
I think I get that. I don't have a long enough cable. So low, yeah.
Okay.
Yeah. I've it's not totally related, but I've read a couple of your papers on impact synthesis. Because I'm talking about roughness. Yes. So there'll be some.
I'm very curious.
Yeah.
Some examples and so on.
Yeah. So I hope the room is interested, but I'm sure you'll have a hard question. Because you know.
You don't think.
We try to show as many sound examples as loud because you can always read the paper.
Yeah.
But the sound. Oh yeah.
Hello, I'm Antonio. I'll be the next. Nice to meet you.
I use them as well, and there are also many websites
I was going into a complicated solution. I just leave it here.
That's a difficult.
Another question. If your period allows the model to I know. I guess that it will be hard to get some answers from the maybe if you're maybe the novelty should not be
in order to do that, we need to all data of this. Yes,
it's for me.
everybody. I'm Mitsuko Aramaki from Marseille, from Physics Laboratory. And so we are starting the second session of this morning, dedicated to audio signal processing. And the first presentation was made by Jeremy Irkas. And we talk about the algorithm for roughness control using frequency shifting and attenuation of partials in audio. The floor is yours.
Thank you. Okay, mic works. Sound. Sound. Works. Perfect. We'll hear that sound a few times. So hi everybody. I'm Jeremy from Music Department of UC San Diego. Nice to see you all. So this talk is primarily concerned with the control of auditory roughness. So I'll just give a brief primer. So auditory roughness is a phenomenon that occurs when sinusoidal sound partials fall in the same critical band of the ear. So it's related to beating. So when sound partials have a small difference in hertz, we hear this slow, consonant beating sound. A little loud. As partials grow farther apart in hertz, we start to be able to, or we lose the ability to count the beats, and we just perceive this sound that we describe as roughness. Sorry for your ears. And as the partials eventually leave the same critical band, we perceive them as two different tones. We don't perceive roughness anymore. Beautiful. So, in the context of music, roughness has been studied often in the context of sound combinations. So, for example, what's the roughness of a musical chord, of harmonic sounds? What's the roughness of a sound mix? And there have been several applications to minimizing the roughness of sounds, which is typically done using pitch shifting. So, for example, we can change the fundamental frequency of notes in a chord automatically. This is done by William Sethris. So just as an example, you might take this sawtooth major 7th chord that you'll hear a few more times in equal temperament, and you might put it into, let's say, just intonation, so that harmonics land on top of each other, reduce roughness in that way, although you do, let's say, substantially change the timbre of the original sound. There's also a little bit of work of actually pitch shifting songs that are going to be combined in a DJ mix by finding the ideal pitch shift is being found as the one that has the minimum overall roughness, which is interesting, by Gebhardt and associates. And what I'm looking at is there a way for us to control the roughness of sound combinations as a musical parameter without basically pitch shifting or changing the fundamental frequencies? So we might take the sawtooth chord, and now just listen for the beating patterns. We might make it less rough, which is subtle, or more rough, which is less subtle. But I have some composition friends that actually want to do that kind of thing. So how we're going to go about this is, instead of pitch shifting sounds, we're actually going to go and adjust sound partials. So to do this, first we're going to need a model of roughness. So if you've ever studied roughness, or sensory consonance or dissonance as it was originally called, you may have seen plots like this, which show for various pairs of sinusoids the roughness that occurs as their distance in hertz increases. Basically this plot shows that the point of maximum dissonance or roughness is different. Here it's plotted as frequency ratio. You can also plot it as difference in hertz. It's different for different portions of the frequency domain. This is because that point of maximum dissonance is related to critical bandwidth. This is a famous result from Plump and Lavelt. So to do this kind of plot, we have, from William Sethris, this is an older model, but it's a mathematical computation of roughness that essentially takes the distance, or the difference rather, in hertz of two sound partials, and introduces this scaling factor up in our difference of exponentials here, so that we can calculate this point of maximum roughness differently depending on where we are in the frequency domain. Sethris's model also has this multiplicative aspect out front, which is, so
to be clear, this is calculating the roughness of two partials, two sine tones essentially, each with a frequency and amplitude. So this multiplication shows that quieter partials or quieter sound partials contribute less to the overall roughness of the sound. And in the most simple model, you basically calculate this for every pair of partials in your sound, sum it up, and that gives you the overall roughness of the sound. There's a lot of derivation and parameterization here that you should check out the paper to see how he fits the Plainchant model. But we can use this to quantify the roughness, and in particular, the roughness that a particular pair of partials contribute to our sound. And once we can do that, we can start thinking about how are ways that we might control the roughness of a sound by changing parameters of individual sound partials, and what might that do to the sound, to the roughness of the sound, and then also what might that do to the rest of the sound that we may want to avoid. So for example, let's consider a pair of partials and what we might do. So here I've plotted our roughness curve, and say that we've got, I've plotted it twice. Say we've got this blue partial, this blue line here that sits somewhere in the frequency domain, and we've got this red partial that sits somewhere close to it, above it in hertz, and it's contributing, these pairs contribute roughness to our overall sound, and maybe we want to do something to the red sinusoidal partial based on this model. There's a problem, which is that naive solutions may lead us to do things that are a little bit too simplistic and actually will collapse our spectra. So if you look on the left example, if we wanted to change the frequency of this red partial to reduce the roughness, the simplest thing to do is actually to just move it over and set it to the same frequency, but now we've lost some of our sound complexity. And similarly on the right side, if we were to, instead of the frequency, if we were to mess with the amplitude, well, we could just attenuate that partial, right? And now we have no more roughness from it, but we've lost our sound complexity. So instead, we can consider doing things that will reduce the roughness, but try to maintain the some of the original timbre and also the power. So if we're changing frequencies, perhaps we only allow frequencies to move some amount in the same critical band so that they stay kind of where we expected to hear them before. If we're doing sound attenuation, maybe we don't completely attenuate a partial, maybe we only partially attenuate it. And maybe we also take the power that we've lost by attenuating some of our sound partials and add it to the other nearby partials so that we maintain the power of our signal, but we have less roughness. So these are just things that we can do on individual partials of the sound. But we can start thinking about what might we want to do to our sound to control the roughness of it over the entire spectrum. Which leads to two algorithms that I developed to try this out. So the first is called frequency bashing, with respect to Miller Puckett, who did phase bashing, which is kind of related. So this is a greedy algorithm that you can use to reduce or increase the roughness of partials of sound by changing partial frequencies. So first, this is a theoretical, assuming that we actually have all of the parameters of our sound to mess with. And the algorithm is quite simple. It is to take all the pairs of sound partials and analyze them using the Seth's model of roughness. So we're comparing all the pairs of partials in the sound. We'll sort them by maximum, what contributes the most roughness. And we'll take one of the partials, and I by default use the quieter partial, and bash its frequency, change it so that it contributes less to the less roughness to the overall sound. And then we're going to mark these partials as already adjusted. And so as we proceed to the rest of the list of pairs of partials, we won't keep readjusting sounds back and forth. So there's no guarantee of optimality, but it does reduce the overall roughness of the sound. So for example, if we had our major 7 chord with its original spectrum on the left, the points are also color-coded by which notes they came from. That's of interest to you. We can see that after we do some frequency bashing, we have some of these pairs of partials like demonstrated on the right, where these partials have just had their frequencies adjusted a little bit, either lower or higher depending on which partial they were kind of clashing with. And this leads to a pretty similar spectrum as before, but just with a different beating pattern. I'll play this for you one more time, and then I promise we'll hear more interesting examples. Original. I hope it's loud enough in the room. It's very similar. There's just a slight difference in the beating patterns. Okay, so similarly, we can change the amplitudes. Which I call amplitude whacking. Why whacking? Well, because you quiet one of the partials down and the other one pops up, so it's like you're playing whack-a-mole. So this algorithm is essentially very similar. You analyze the pairs of partials and you sort them by maximum roughness, and now instead of adjusting the frequency, you adjust the amplitudes. So if we look at the same spectrum as before, now we have these pairs of partials like this, where one of the partials has been attenuated by, it looks like about 7, 8 dB, and the other one has been increased by 1 or 2 dB. And this audio example actually is not as interesting to listen to, but I'll show you a more interesting one later. So that's theoretical. But what if we want to actually make some sound examples? And in particular, what happens when we want to do this with audio signals? In an audio signal, we might not have the actual partials of the sound sitting right there for us to adjust, but we can do things like sinusoidal modeling to understand what partials are in the sound, particularly where they're most prominent. There's a problem. Roughness, even though it depends on the frequency range, when partials are like 20, 30, 40 hertz apart, these are our kind of areas of maximum roughness. These are a little bit hard to pull out in analysis, and actually even harder to pull out to, like, say, filter in a sound that's already a mixture. But one idea is that, I showed these previous applications of roughness are usually applied to sound mixtures, so either combinations of notes or combinations of signals. So what we can do is look at signals that are going to be combined in a mix and analyze their partials, and then only consider partials that are going to introduce roughness between signals, so that we have a little bit more access to understand what's going to happen when we put these together. So to run these algorithms in audio, there's a little bit of pre-processing. We'll take our signals and we'll do some kind of sinusoidal analysis to understand the most prominent partials in the sound. And we'll determine partials between signals that overlap in time. So this is a straightforward example. And we'll consider the partials that are from one signal against all the partials in the other to consider whether or not one of these partials needs to be adjusted to reduce or increase the roughness in the sound. Additionally, to actually process it, what we will do is, using the sinusoidal analysis, we'll create these pairs of amplitude complementary notch and peaking digital filters, and we'll process these signals so that the original signal will be sent through this series of notch filters to try to isolate these sinusoidal partials, and then in parallel we will put them through these peaking filters to isolate the partial we're interested in, and then change the partial by processing the output of that filter, either using single sideband modulation to change the frequency, or just gain to change the amplitude. There is also an implementation of this in Max, which I may or may not have time to show you. Implementing it in Max is straightforward in an additive synthesis scenario, because you already have the parameters that you're going to be using. And you can, my implementation, it only runs at control rate because of the sorting and a few other things, but you can use the multi-channel signal objects to perform additive synthesis. And there are actually some slight tweaks to the algorithm to save CPU, but those are in the paper. So I've only got about a minute and a half here left, and I would like to show you some sound examples, because these are the most interesting parts. What can we do with these algorithms? One of the most interesting things, I think, is to basically use it as like a production tool, reduce the roughness automatically in sounds that are going to be mixed together. So here I'll play you a horn line. There were a couple of parts there. I'll try to point out, this is the amplitude adjusted version. And if it was a little hard in the room, we can listen to actually what changed. So it's a lot of work to do something subtle, but if you listen in headphones, it's actually, it's quite apparent. We can introduce roughness to sound combinations, so you can take your beautiful chord and mess it up, which is a pretty extreme example, but I find it kind of interesting. There's a couple of other audio applications with regards to like frequency, domain-specific tremolo, and also alternative to combining notes with complex timbre, which if you ask a question about that, I can play my video example. But otherwise, it's online, and I don't want to take up too much more time, so thank you for your attention so far. There's more examples, and the code is available, and yeah, thank you.
Thank you, Jeremy. Any questions? Yes?
I actually have a question about like perception more than anything, because I mean, you can eliminate roughness, but in a performance, live performance, it depends on the performance, right? So
sure.
Your action might actually change the actual sound that you would have heard, I don't know, in the village bar or Blue Note, depending on the environment. So can you comment on this?
Yeah, so you definitely change the, you change, so the roughness is just one perceptual feature, but changing the roughness too much can definitely change other perceptual features. With regards to live, I don't have a good way of doing this algorithm live, actually. It requires a full analysis of a signal, unless you're just doing something like additive synthesis, then you can actually control the parameter live, which is pretty interesting. But yeah, there's many other perceptual features that are not necessarily accounted for here. Sorry, I don't know if that fully answered your question.
Yeah, but we get more.
Okay, yeah, that sounds great. Thank you.
Other questions? Yes?
Oh, Marcelo. Play my video example. Okay, here. So this is from William Sethers' adaptive tuning, actually. So here is a complex. That's, believe it or not, a C major chord, but it's with a stretched spectrum. So I will play this, and then I will frequency bash it. You can hear what changes. It's a more consonant sound. The timbre changes more substantially, but sorry, I'm talking over this. But then I'll show what happens when you adaptively tune it using William Sethers' algorithm. Right here, which is quite substantially different. And then the frequency bash version is somewhere in between. And then that's the original again. And this is the amplitude adjusted version, so the frequencies are exactly the same, but the beating pattern is different. Again, that's the William Sethers version. So, neither is better than the other, but it's different ways of taking a very complex and rough spectrum and adjusting it right on the fly. Yeah. Thank you, Marcelo.
Other questions or comments? Yes,
I was just wondering if when you add and remove components, you might have some masking phenomena that means that you might not hear the difference, or you can also maybe create some combination tones that you didn't expect. Do you have some surprises sometimes when you play with the spectrum?
I have not experienced any combination tones yet, although I think absolutely you could do that. One surprise I had actually is that sometimes in changing sounds you find when you move partials away from each other, for example, sometimes you really hear that, wow, like this trumpet sound is so complex. There's a real strong sinusoidal component that I wasn't hearing before, which you may not actually want, but it's interesting. I do want to point out with regards to masking, this is a bunch of equations, but when you adjust the amplitude, actually, it's actually a slider. It's not just a do it. And the slider ends, so to speak, when one partial completely masks the other. So you can actually play with that parameterization. Yeah. And there's some equations for how to do this that are in the paper. Yeah, thank you.
Last question or comment? Yes, I have just a question about when the signal varies over time.
Mm-hmm.
How do you manage the
Vibrato and notation. Yeah, so I don't have a good answer for that at the moment with signals. I need to think about what's the right thing to do there. The max implementation, if you did like an analysis and resynthesis, will handle that because you're just getting the partials in time. But it's kind of funny because there actually gets to be like a stickiness. Like if you imagine you're down here at this note, and then you sort of glissando up to this note, and if there's some other thing happening in the sound where roughness would be introduced right in the middle, some of the partials will kind of it's like they stick down here, and then as soon as you pass it, they shift up here, which is kind of cool or kind of annoying depending on if that's what you want in your sound. Yeah.
And a quick last question. Have you seen the Lehman model of roughness? Have you considered this model? Because it's by Mark Lehman. He proposed a roughness model, and you have the roughness over the time and over the frequency also, so it's more rich, and you can compute the roughness for real signals.
Yeah. I'm not sure if I know that specific model. I've looked at other models. This model from William Fethers is quite old and has been modified and made more accurate by many people. I do find in using more complex models, it was sort of like using more complex computation for not a huge difference because this is just the creative application didn't change so much, even though the actual model of how we experience roughness was more accurate. But there might be some totally different model that would be interesting to try. Yeah. Thanks.
Thank you, Jeremy.
Thank you.
So we move to the next presentation. It was made by Antonio Sapinto, and the study was made with Gilberto Bernardes. And the talk is about bridging the rhythm gap, a user-centric approach to beat tracking in challenging music signals.
Okay. So good morning to everyone. My name is Antonio Sapinto. I'm from University of Porto. And I'm really happy to be here in CMMR Tokyo. And so let's start. Let me first set the context of our research, as this is a rather cross-disciplinary gathering. And so to set particularly the main domains where our research grows from, we set ourselves in content-based music information retrieval, and particularly we try to harness human-in-the-loop machine learning techniques to tackle rhythm analysis in audio music signals. We are particularly focused on challenging musical examples where even the state-of-the-art underperforms. We are mainly focused here on the task of beat tracking, the foundational task of beat tracking. A brief quantitative snapshot on where we are on beat tracking research. So here in this image we can see the last four state-of-the-arts spanning roughly the last 10 years. And by looking into these results from from these different data sets that are cover quite a lot of mainstream examples, we could say two things. First, that it's almost or pretty much solved. So we have F measure at least here in, for instance, for the ballroom, almost 96%, which is really good. And the second thing is that we don't see a great improvement, but this only shows that we are reaching the ceiling, and so this is a game of diminishing returns, of course. The problem lies in here, when we include the SMC dataset, and this dataset was made to test bit trackers, to select really challenging examples. It was proposed in 2012 by Olzapfo and Associates. And so the first thing we see here, we see that we move from almost 0.9 to roughly 0.5, which is clearly different and not very good. And also the second thing we can see, if we enlarge this analysis to almost the last 20 years, we can see that we did not move that much, only 20 percentage points. So we can say that we are pretty much more or less where we were in 2014, at least regarding these challenging examples. So we are far from being on par with human bit perception. We now focus on the current state of the art in what regards to bit tracking, and it's our departing model and our baseline, let's call it so. And here let me show some examples of what happens in the state of the art. What's the output of the state of the art? In this image, okay, on the upper plot, on the upper subplot, we have the input spectrogram to the network, and on the lower subplot, we have these two parts. So first we have the bit activation function, so the prediction of the model, and these lower parts, we make this to focus on the user perspective. So here we are trying to measure the performance of the bit tracker regarding the correction annotations a user has to perform to correct all those bit outputs. So we focus here on this lower part on the number of correct detections, shifts, deletions, and insertions from the state-of-the-art output. And we have here this panel where we summarize these measures, and we include also the F measure. So here, I'm sure, now that I showed this, let me show how this performs with an arrangement on a Japanese folk melody. So what we see here, this is not a particularly challenging example, but we see some expressiveness, some tempo expressiveness that really makes the state-of-the-art perform with a F measure of 0.45, which is somehow low. So a user, if he wants to perform the track on this track, he would have in the end to make 27 manual corrections to this, which is highly costly. So let me show you just two more examples. Another one that should be simple to analyze because it's very markedly, it has strong onsets and very marked. So here we have even worse in just 40 seconds, the user would have to correct 61 bit operations from the current state of the art. And then finally, the extreme case. Okay, in this case it's even more strange because it's electronic music. You would expect it to be really easy. The tempo is completely steady, but the state of the art from its standard operation completely fails because it is offsetting 180 degrees. It's grabbing into the upper mid tempo. So that's the problem that happens here. So these examples showed what the classical musical content challenges for bit tracking that are very known and very much focused on the signal part. Also, another problems that are really very much increased with the current deep learning paradigm, which is very data intensive. And this means what? This means that for genres that are underrepresented in data sets, the performance of the automatic bit trackers is low. So we cannot. We need to annotate them manually. So that's very costly. We don't do that, and they don't go into the data sets, and they don't go into the models that are trained on these data sets. So we are kind of stuck in this loop, and is clearly a bottleneck in this situation. So this has many implications and a clear impact. In our work, we focus on rhythm, and that's important because it's completely pervasive in numerous music cultures, particularly from African origin, and we try to fight the User-Centric bias of MIR, music information retrieval, which is very known and very much studied and revealed in literature. So we try to make this bridge into the domain of computational ethnomusicology and try to port the tools and the state of the art to these challenging genres that are not present in nowadays data sets. So the problem is, from the user perspective, what can we do when even the state of the art fails? And this could be the question of ethnomusicologist researcher. Our approach is that we think that user knowledge should be leveraged for adaptability of these leading MIR methods. Sorry. Okay, we follow a big trend in literature. Some of these are works that were done in parallel with our own, but mainly we move from a system-oriented point of view to a user-centered point of view, and we make the user just fine-tune a little snippet of 5 seconds and annotate the bits in those 5 seconds of audio. With that, we parameterize the post-processing common part of this deep learning state-of-the-art methods, which is usually the dynamic Bayesian network. And we do this in a very short period of time. This is very fast, and we can do it in our own personal computers. So the applicability is, we focus on bit tracking, but it's transferable to other tasks. And although we depart from this TCN-based model, it's applicable to other models that imply, of course, training on data. here is just a snapshot of our previous results, and we focus here on the SMC dataset, where we can see in all datasets, but particularly in the SMC, better results. So a move in the vertical direction means the performance of our approach is better than the baseline, which is the state of the art. And here we can see the before and after the baseline result on the Sakura example that I showed you. It was .458. It goes into .6789, and so we can have really good improvements in terms of F measure, and also we focus here on the improvement of the number of operations we have to do after our approach compared to the number of operations of the state of the art. So the improvement is really clear. Here, just to let you know that here we are showing also the part that we use for fine-tuning, which is just 5 seconds, then validation 5 seconds, and we test on the rest of these examples. So we have here some examples with different types of errors and different improvements, and the electronic examples are the ones where we get higher, and this is particularly phase offsetting. It's a problem of phase offsetting of the baseline. So in moving into more challenging musical contexts, we focus on these 3 examples: Colombian Bambuco, Uruguayan Candombe, and the Steve Reich piano phase, that focus on 3 examples of rhythmic dissonance: polyrhythms, polymeters, and polytempi. Probably I don't have time to this, but let me. So the results are equally relevant. We can see the baseline improves a lot, much more in the compound. This is a biometric genre. So when we use the compound annotations, we see a bigger improvement. And let me try to, okay, so Uruguayan Candombe, this is a highly syncopated polyrhythmic. Also, it doesn't seem really difficult, but the state-of-the-art struggles, and here we can see an improvement from 28% to 95%, which is really clear. Finally, we try to put the tests into a polymeter, so we are going against the own definition of beat tracking, where we try to focus on a pulse, and here we put ourselves to the test trying to focus on 2 contrasting pulses. So I won't have time to show you this, but I'm sure most of you know the time is up. Okay. So this is it. I can just conclude with this summary. I hope Marcelo asks me to show this in a while. But just so this is the conclusion. Sorry for late time. Okay.
Thank you, Antonio. Just because before the question, we want to hear the Colombian one, maybe, because it was the most interesting at the end.
Yes. Sorry, I.
No, not that one. The Colombian one.
The Colombian
The Colombian one. Sorry.
Yeah, we can see the video after.
Okay. So you can think of it in simple 3/4 or in compose 6/8. So, and the annotations are double. So we have the data set annotated as a simple simple meter or a compound meter. So thank you for letting me show this in great detail.
And the video?
Thank you, Marcelo. So this is a really hard, really challenging for a beat tracker, but we were able to go from 0.2 in F measure to 0.7, which is really good for such a difficult example.
Any questions, comments? Yes?
Sorry, maybe I missed one part. That how do you do this? I got that you got much better F score. Do you retrain them, like?
Yes, it's just fine. We do two things. We fine tune. We use a snippet of 5 seconds of the user annotates. So we use that to fine tune the model.
That's enough for this example. That's fine.
Yes.
Okay.
And we use also that to parameterize the dynamic Bayesian network, which the state of the art has. So we don't develop a new model, we just fine tune and parameterize the existing state of the art.
Okay, so about the model and also the DBN parameters
Yes.
change. Okay.
Yes.
Thanks.
Yes.
Yes?
Can I just shout my question?
No, maybe the middle microphone.
Can I ask a short one? I'm just right next to here.
Oh, okay, yes.
Yeah. My question is, like, the beat tracking F measures, usually they have different time, different.
We are using
times
70 milliseconds, which is more or less the default. Yes.
The question is about piano phase, because I don't know how much the piano phase deviates, but probably within a short time period you can catch both beats with the same F measure. So
that's a good question. We didn't go into that deep in the analysis. We just tried like the most challenging possible for a beat tracking to beat track, which is to show him 2 beats to follow, and we just think it was enough to show that this improved a lot. So we are mainly focusing in providing a universal improver of state-of-the-art models. So in that sense, we didn't go into much in detail, but you are right in that, and that's interesting. There are parts where we would accept it because they are just inside these 70 milliseconds. Yes, but we are mainly focused on comparing performances, okay? And in that terms, we really improve a lot. Okay.
Thank you.
Thank you.
Now for my real question. Did you check if the performance of the system on the rest of on the other databases and everything, when you fine-tune the system, if it messes with the performance or if it keeps the performance?
Okay, I tried to show, okay. Sorry. Sorry, my computer is really slowing down here. Okay, here you can see the performance in all the 4 data sets is improving in all musical examples. And this is done only with these 5 seconds fine tuning and then some parameterization that's very easy to do. So this is good to improve almost everything.
Thank you.
Thank you.
Yes,
your method could be applied to other MIR tasks?
Surely. We already applied it to other tasks on set detection. So in the Bambuco case, it gets obvious that it can be applied to meter determination, because that's what we are doing underneath. And musical segmentation comes across, but other, I would say, tasks where there is high degree of subjectivity. So the user, it makes sense for the user to try to impose his opinion on the model. So yes, but we are mainly focused on rhythm because it's highly subjective in several aspects. But yes, and this is being done in. So this, let me. Now I don't know if I can find it. But there are other works. So this is on this big area regarding transfer learning. That's the main thing. Also few shot classification. It's highly related. We see some other examples of the same type of techniques using for interactive musical bit tracking, for on-set detection from many tasks. Recently for musical segmentation, this will be when you don't have a notation power to solve a task, and that will happen a lot with this, for this ethnomusicology analysis. This will always happen. You have to resort to this type of techniques, and it works, and it's simple.
And the last question?
Maybe I can ask my question.
You can ask it? Okay. So the time is up, and it's already the end of the session. So we can thank again the two presenters.
Hello again. Okay, hello. Don't you have a hangover? Okay. Actually, I have. Okay. So anyway, I will start today's 1-minute summary talk for posters. So please come to posters presenters here. And I have one announcement. So one poster by Richard Lindell, which was originally assigned to yesterday's poster session, has been moved to today's poster session. Okay, Madoka-san, and Sai-san here, and Stefano, okay. And then Thomas-san, okay, and Riku-san, and Emilia-san, and Eve.
Yeah.
Okay. Then Arika, okay. Okay, so the rule is actually same as the yesterday and this on. And so please present your work summary within 1 minute. Your summary slide will be projected with this PC. So once your slide appears, please start your talk. If your talk exceeds the 1 minute limit, the chair will stop your talk. After your talk, please pass the microphone to the next presenter. Okay, and then, so there are no summary talks for demos. Instead, I will announce their titles. Okay, please start.
Hi, I'm Hirota from Tokyo State University. Today I will talk about creating a new lullaby using an automatic music composition system in collaboration with a musician. Many mothers with young children have worries and stress about putting children to bed. Therefore, methods tries various methods. For example, read a book, sing a lullaby. A Japanese publishing company published sleep-inducing picture book and planned to create a promotional video with pictures from a book and new sleep-inducing lullaby. In my poster session, I introduced automatic lullaby composition technology and case study of collaboration with professional musician, Buffy. Thank you.
Hi everyone. Today I'm going to introduce our research that automatically gives information on a score and generate expressive performance. To get phrase information, we use GTTM, the generative theory of tonal music. In this theory, there's a hierarchical tree that means the shallower node is more structurally important in the music. We assign phrase from each of these subtrees and propose some algorithms. And to evaluate, we use director music DM, which can generate expressive performance from phrase information. Thank you.
Hello, my name is Sayosa, from Nihon University. My study purpose is to create a system for flutists that show correct growing style. For create this dataset, in this time I introduce dataset that includes sound, evaluation, and level of growing style. For create this dataset, we conducted performance experiments and subjective evaluation experiments. I will talk about detail of our experiments and example of how to use dataset. Please come and listen. Thank you.
This is the 1-minute presentation for melody blending, a review and an experiment. The paper, presented in poster format, describes our experiments with the task of blending 2 melodies into a third. The domain is symbolic and we consider 2 melodic blending tropes, adopting a dichotomy originally proposed in the raw audio domain, hybridization and morphing. In reviewing what has been done so far, we lament a lack of standardized evaluation procedures. To this end, we propose a set of evaluation metrics that might be useful to compare different melodic blending systems. Then, representative methods used in some of the latter are re-implemented and adapted, and tested according to the evaluation procedures put forward. Come along to the poster session to find out more. Thank you.
皆さん、2回切ってください。
Hello, my name is Thomas Odelin, and our team from the Georgia Institute of Technology is proposing this system called Mixboard. It is an app that allows musical novices to create mashups of up to any 4 songs that they would like off of Spotify. And we've spent a year studying how these novices interact with the AI and what they think about the co-creativity and learning process. So I'd love to see you all upstairs and hear what you create. If you click again, you can hear what one of our users created too. Do you mind clicking this slide? Okay. Well, if the video isn't working, you can come upstairs and create your own mashups.
So this is the PDF file, actually.
That will do it. Okay, never mind. Thank you.
Hello everyone, my name is Rick Takashi. I'm from Future University Hakodate in Japan. This global prediction of time span trees by fill in black task. Our motivation is to understand the relationship between time span trees, subtrees. When listening the music, humans are to be analyzing and predicting at the same time. Symbols or present or code progression or etc. We saw that this mechanism exists through GTTM. This requires not only local relationship but also global relationship. Hand over. Thank you for listening.
Hello everyone, my name is Emilia Parada, and together with my co-author Maximilian Schmidt, we're going to present our work entitled Music, Emotion, and Solopiano, Plainchant between Human Perception and Machine Learning. I come from the Music University of Music in Nürnberg University of Music in Germany, and this is a joint work with Anton Batlina and Björn Schuller from the University of Augsburg, also in Germany, as well as Markus Schödel from Johannes Kepler University Linz in Austria. We're going to try to answer two questions, and these are: which are the most appropriate multimodal features to automatically identify emotions perceived in piano music? That means we work with both symbolic features and audio features. And the second question is about whether we can extend or generalize our results, and for this we run experiments on the Mopia dataset. Thank you.
So I'm Craig Sapp from Stanford University, and I worked with F. Poudre at University of British Columbia, along with their students Brian Bell and Jason Lee, on an experiment to look at emotional effects of polyrhythm as part of the Polyrhythm Project. The poster presents results of listening experiments examining how polyrhythm descriptive features are perceived in terms of mood, energy, movement, dissonance, and tension. So the study also examines the effects of synthetic stimuli versus audio recordings, with an interesting finding that synthetic audio was perceived as more positive in mood and less tense than human performances. So I can also demonstrate the polyrhythm data set, which contains 800 samples of polyrhythm from early 20th century composers. And this slide demonstrates the ability to automatically highlight and analyze polyrhythm on the website. Thanks.
I am Rickard Lundell, and together with Henrik Frisk, we authored The Unfinder, Finding and Reminding in Electronic Music, a pilot study. Today's file systems were designed for text files, and from the literature we know that users still rely on file navigation and use portable storage devices. To understand our artist-managed material, we collected journals analyzed with thematic analysis. Artists use a plethora of methods that differs from the literature, and we found 6 themes: media storage, structure, metadata and collection of material, data, time and remembering, matured material, associations, and tool. Talk with us to find out more and what they mean. And furthermore, we'll play modular and saxophone at the Jazz Spot Candy tomorrow at Friday, 7 p.m. Jazz Spot Candy tomorrow, 7 p.m.
Thank you very much. And then, so we have some demos. Let me introduce today's 9 demos. One is so from J symbolic to N3, more musical features, comparing vocoders for automatic vocal tuning, music recognition, encoding and transcription, Muret online tool demonstration, microtonal music data set 3.1, lightning control based on colors associated with lyrics at bar position, and melody changing interfaces for melodic morphing, relative representation of time span 3, zero-shot music retriever for Japanese manga, and visualizing musical structure of house music. Okay, so everything is same as yesterday. So we have 2 rooms. So in larger room, we have all posted sponsors booths and 2 demos. And in a smaller room, so we have 7 demos. The time is 1:20 p.m. to 2:40 p.m. And this is the details of the room layout. And this is the layout of smaller room. Okay, so enjoy lunch and come back before 1:20 p.m. Thank you very much.